Any real-world problem that involves a rate of change, and they range from marginal costs in economics to objects in motion, including the position of planets in the universe, are represented by differential equations. The invention of differential equations enabled mathematicians to solve problems that had befuddled them for centuries. Hi, my name is Jason Rosenberry, and that's what we are going to investigate in today's lesson. Let's start with the definition. Differential equations. An equation involving a derivative is called a differential equation. The order of a differential equation is the order of the highest derivative involved in the equation. Let's work an example. Find the general solution to the exact differential equation dy dx equals 5x to the fourth minus secant squared x. So here's our original equation, dy dx equals 5x to the fourth minus secant squared x, and it turns out that the solution is simply the antiderivative, or imagine integrating both sides of the equation with respect to x. So on the left hand side we're left with y, and the antiderivative of the right hand side we would have 5x to the fifth over 5, which is just x to the fifth, and the antiderivative of negative secant squared x would be negative tangent x, and we have to have plus c representing some constant that we may have on the end. So again, this is what's known as the general solution to the differential equation. If the general solution to a first order differential equation is continuous, the only additional information needed to find a unique solution is the value of the function at a single point, called the initial condition. A differential equation with an initial condition is called an initial value problem. It has a unique solution called the particular solution to the differential equation. Let's look at an example. Find the particular solution to the equation dy dx equals 3 sine x, and let's say that we're also told that y is equal to 2 when x is equal to 0. Here's our given information, dy dx equals 3 sine x, and we know that y is equal to 2 when x is equal to 0. So let's start by finding the general solution, which again is simply the antiderivative. So that would tell us that y is equal to the antiderivative of 3 sine x, which would be negative 3 cosine x plus some constant. And now we can use the initial value information to figure out what our constant c must be. So let's substitute the values in for x and y. So y is 2, and that happens when x is 0, plus c. And now we solve this. Cosine of 0 would be 1. So 1 times negative 3 is negative 3. Adding 3 to both sides, we get 5 is equal to our constant. So let's now take this value for c and substitute it back into the general solution. Therefore, our particular solution would be y equals negative 3 cosine x plus 5. Now it's time for you to try a problem. Find the particular solution to the equation. We have the equation du dx equals 7x to the sixth minus 3x squared plus 5. And we're also told that u is equal to 1 when x is equal to 1. Pause the video while you work on this problem. When you are finished, restart the video to check your solution. So here's our given information. Du dx is equal to 7x to the sixth minus 3x squared plus 5. U is equal to 1 when x is equal to 1. Let's begin by finding the general solution. So u would equal 7x to the 7th over 7, which is just x to the 7th. The antiderivative of negative 3x squared would be negative 3x to the third over 3, or negative x cubed, and then plus 5x plus constant c. Now we'll make our substitution. So u is equal to 1 when x is equal to 1. So that's 1 to the 7th, which is 1, minus 1 cubed, which is 1, plus 5 times 1 plus c. So when we solve for c, we get c is equal to negative 4. Now we'll take that value of negative 4 and now we'll substitute it back into the original equation, giving us the particular solution u equals x to the 7th minus x cubed plus 5x minus 4. If a curve is continuous, the initial condition determines a particular solution for which the curve passes through the given point and pins down the solution on the entire domain. If the curve is discontinuous, then the initial condition pins down only the continuous piece of the curve that passes through the given point, in which case the domain of the solution must be specified. Let's show an example of that. Solve the initial value problem explicitly. We're given dy dx equals negative 1 over x squared minus 3 over x to the 4th plus 12, and y is equal to 3 when x is equal to 1. So we have our given information, dy over dx is equal to negative 1 over x squared minus 3 over x to the 4th plus 12, and we also know that y is equal to 3 when x is equal to 1. To help with the anti-differentiation, let's rewrite our derivative using negative exponents. dy over dx can be rewritten as negative x to the negative 2 power minus 3x to the negative 4 power plus 12. Now let's find the antiderivative of both sides of this equation. The antiderivative of dy over dx is y. The antiderivative of negative x to the negative 2 power will be negative x to the negative 1 power over negative 1. The antiderivative of our next term will be minus 3x to the negative 3rd power over negative 3, plus the antiderivative of 12 will be 12x, and we cannot forget plus our constant c. Simplifying, we now have that y is equal to 1 over x plus 1 over x cubed plus 12x plus c. Now, to find our constant c, we will use the information that we know that y is equal to 3 when x is equal to 1. Making those substitutions, we would have 3 is equal to 1 over 1, which is 1, plus 1 over 1 cubed, which is 1, plus 12 times 1, which is 12, plus c. This implies that 3 is equal to 14 plus c, which implies that c is equal to negative 11. We will now substitute our constant c equals negative 11 in for c to give us y is equal to 1 over x plus 1 over x cubed plus 12x minus 11. And we must also add the stipulation that x must be greater than 0. Sometimes it's necessary to use the fundamental theorem of calculus to solve an initial value problem because we are unable to find the antiderivative. Let's take a look at an example. Solve the initial value problem using the fundamental theorem. We have dy dx equals sine x squared and y is 5 when x is equal to 1. So here we have the given information. dy dx is equal to sine x squared. Y is 5 when x is equal to 1. So using the fundamental theorem, the part 1 part, that part of the fundamental theorem, we can write the following. We know that our function y is equal to the definite integral from 1 to x of sine t squared dt plus some constant c. Now, let's see what happens if we were to let x equal 1. If x is equal to 1, we know that y is equal to 5. So this would imply that 5 is equal to the definite integral from 1 to 1 sine t squared dt plus some constant. And what do we know about this definite integral right here? Since we're integrating from 1 to 1, we know that that underlined expression is equal to 0, implying that 5 must be our constant. So now we'll make that substitution, giving us the final answer that y, or f of x, is equal to the definite integral from 1 to x sine t squared dt plus 5. Let's explore graphing the general solution to a differential equation. The general solution always has a plus c as part of its function. Recall that the graph of y equals f of x plus c is simply the graph of y equals f of x shifted vertically by c units. Since c is a variable, we get a graph of family of functions. We can graph some of the functions that are part of the family to illustrate the idea. Let's look at an example. Graph the family of functions that solves the differential equation dy dx is equal to cosine x. So we have dy dx equals cosine x. The antiderivative would be y is equal to sine x plus some constant c. Since there's an infinite number of possibilities for that constant c, we cannot graph all of them. However, we can graph some of them. So let's use the following keystrokes illustrated on the right hand side to graph a few of these infinite number of possibilities. So enter those keystrokes into your calculator and press graph, which yields the following. So as you can see here, the equation y equals sine x plus c, where c is a constant, yields the following family of graphs. When c is equal to 0, we have the regular basic y equals sine x graph, which I'll trace in red, which is the one you're probably most familiar with. This is the classic y equals sine x graph. And now, by simply changing the c value, that would give us a vertical shift of the graph of y equals sine x. So the equation y equals sine x plus 1 would move the red graph up 1 unit. So this would be y equals sine x plus 1. And if we wanted this one right here, we would have that as y equals sine x. And that one we shift it down 2 units, so that would be y equals sine x minus 2. The differential equation gives the slope at any point x comma y. We can use this information to draw a small piece of the linearization at that point, which approximates the solution curve that passes through that point. Repeating this process at many points yields an approximation of the family of functions called a slope field. For example, construct a slope field for the differential equation dy dx equals cosine x. So let's look at some specific values of x and calculate y, which represents the slope of the curve at that x value. So for x equals 0, y equals 1. Let's go back and see exactly what that is saying. Notice here that at x equals 0, the slope of the tangent line is 1. No matter where we go, up or down, choose any of the graphs in that family of graphs, go to x equals 0, go up till you hit the graph, and the slope of the tangent line at that point is equal to 1. For x equals plus or minus pi, we would end up with a series of tiny segments with slope -1. For x equals pi over 2 or negative pi over 2, y is equal to 0. So there we would have tiny horizontal segments with slope 0 along the lines x equals plus or minus pi over 2. At last we have x equals plus or minus pi, and the slope of the tangent lines at those x values would be y equals 1. So we would graph a series of tiny segments with slope 1 along the vertical lines x equals plus or minus 2 pi. So in doing all of that yields the following graph. So here's our graph that's known as a slope field. And from the previous page we learned that when x equals 0, the slopes of all tangent lines would equal y equals 1. So as you can see, at x equals 0, go up or down, we can see that the slopes of all of these line segments are equal to positive 1. Now let's go to plus or minus pi, where we know the slopes of all tangent lines at plus or minus pi must equal -1. So here we are at positive pi, x equals positive pi, and here we are at x equals negative pi. And that is also true for all odd multiples of plus or minus pi. From the previous page we saw that at x equals plus or minus pi over 2, slopes of all tangent lines would equal 0. So here we are at positive pi over 2. Here we are at negative pi over 2, and that is also true for all odd multiples of plus or minus pi over 2. So as you can see out here at 3 pi over 2, we're having slopes of 0, and also here at negative pi over 2 we have slopes of 0. And then finally we saw that at x equals plus or minus 2 pi we have slopes of positive 1, and out here we are at positive 2 pi, and here we are at negative 2 pi, showing that those slopes are equal to positive 1. So with all of this knowledge, we can kind of now pencil in these families of functions by using these individual slopes of the linearizations. So as you can see, we can kind of connect the line segments indicating the general direction of a curve. So there, the one in red would be y equals sine x, and then as I go up or down, we would have the curves corresponding with each individual different value of c. Again, positive values we would just shift the graph upward, and negative values we would shift the graph downward. Let's construct a slope field for another type of differential equation. Use a calculator to construct a slope field for the differential equation dy dx equals x plus y, and sketch a graph of the particular solution that passes through the point 2, 0. Let's look at the graph that the calculator produces. We see that the slopes are 0 along the line x plus y equals 0. Slopes are -1 along the line x plus y equals -1. Slopes are getting steeper as x increases, and slopes get steeper as y increases. The blue line superimposed on the graph is for the particular solution of the point 2, 0, as you can see that it passes through the point 2, 0, which is right here. We will now examine Euler's method. In the example that we just did, we graphed the slope field and then found a smooth curve through a given point. We could have started at the given point and pieced together little line segments to build a continuous approximation of the curve. This is called Euler's method. Euler's method for graphing a solution to an initial value problem. Step 1. Begin at the point x, y specified by the initial condition. This point will be on the graph as required. Step 2. Use the differential equation to find the slope dy dx at the point. Step 3. Increase x by a small amount called delta x. Increase y by a small amount, delta y, where delta y is equal to dy dx times delta x. This defines a new point, x plus delta x, y plus delta y, that lies along the linearization. Using this new point, return to step 2. Repeating the process constructs the graph to the right of the initial point. To construct the graph moving to the left from the initial point, repeat this process using negative values for delta x. Let's take a look at a diagram that will illustrate this method. Again, you're going to start at the point x, y is given as the initial value point, and what you'll do is, using the slope, find the next point. So as you can see, using the slope, which is the line in red, that's our new point, x plus delta x, y plus delta y. This process is then repeated, stringing along a couple of line segments, small line segments, giving us an approximation to the curve. Let's work out an example. Let f be the function that satisfies the initial value problem of a previous problem. So here we have the previous problem, dy dx was equal to x plus y, and we were told that when x is 2, y is 0, or f of 2 is equal to 0. Use Euler's method and increments of delta x being 0.2 to approximate f of 3. So here's the chart showing Euler's process, Euler's method. We start with the initial point, which we're told is 2, 0. Then the next step is to find dy dx. We're told in the problem that dy dx is equal to x plus y. So we simply add together the x coordinate and the y coordinate. 2 plus 0 is 2. We're told in the problem to use 0.2 for delta x. So again, moving across. Our next step is to find delta y, which is dy dx, which is 2, times delta x. 2 times 0.2 is 0.4. Now we've located the second point. We take x plus delta x, or 2 plus 0.2, giving us 2.2, and y plus delta y, 0 plus 0.4 is 0.4. This is our second point. Notice we take that point and we start over again and repeat the process. So now we go find dy dx, x plus y, 2.2 plus 0.4, 2.6. We're using the same delta x of 0.2. We now find delta y, which then establishes the next point. We're going to repeat this process until we get to an x value of 3. Because we're being told in the problem to approximate the curve from x equals 2 to x equals 3 using 5 linearization segments. So now the last step would be to, starting with 2, 0, plot that point, plot all of these points over here in your last column, and connect those points using segments. So we would see that Euler's method leads us to an approximation that f of 3, looking at our last point, f of 3 is approximately equal to 3.46496. Notice here again, the blue graph is the actual curve, and then we have the series of segments that we just found using our charts, and as you can see, our linear approximations do approximate that curve very closely from x equals 2 to x equals 3. In this case, Euler's method is underestimating. Why? Because the curve is concave up, meaning the curve of the true graph, the blue graph, is concave up, so we are underestimating. And if the original graph would be concave downward, then we would overestimate. The error in this example is about 16.6% because the true value of f of 3 is 4.155. Using a graphing calculator and smaller increments, instead of maybe we used 5 increments of 0.2, if we were to use, say, 100 increments of 0.01, then our estimate would be 4.1144 for f of 3, yielding an error of about 1%. In this section, we explored differential equations, slope fields, and Euler's method. Make sure you work the exercises your teacher assigns, and we'll see you next time.